Well, I think we can get going. Welcome back, folks. Looks like we have a pretty even split, 2 people in class, 2 people in Zoom. So welcome back, everyone. I think this is the nicest day of the year. So this is probably one of the harder classes to make it too. So I appreciate your work ethic. Any questions at all to start us out, folks? Okay, well, we kind of see the announcements here, but let's talk about them anyway. Just seems like a good way to get started. We're getting through section 4.4. We'll probably spend most of the time today working through that section. It's not one we want to rush through. But if we have additional time, we'll be getting into section 4.6 on antiderivatives. So because we're dealing with antiderivatives, I put this document, just a roundup of important differentiation formulas on our notes, because what our goal is to now reverse all of those formulas. In fact, we produce an antiderivative, and somehow, some way, this concept is going to take us to the integral calculus. And we should pause right here. We're getting so close to defining that, we should just say what it's all about right here and now. We should compare it though. If we look at differential calculus, it's all about doing this. You get a curve. Let's just make it start at A, go up to B. Let's make it be just a nice little curve like this. And the differential calculus is all about taking a point, and when you produce a tangent line on that point, let's say it's based off a value, say C, the slope n is the derivative of f at C. So now, what's integral calculus? Integral calculus is doing something that feels totally different, but in a real sense, these are inverse processes. The integral calculus will go from a point A, drop down a vertical line, go to the point B, drop down a vertical line. We have a bound that's under the curve, and the curve itself is a bound. And all we're trying to do in integral calculus is find this. A for area. If we can find that area, we're integrating that curve, finding the area under it. Now, in a really weird and wild way, finding this area under the black curve, bounded by this line, bounded by this line, and the horizontal axis, it's related to the derivative. And if we can find a so-called antiderivative, just reverse our differentiation formula, then we can get that area. So there's a lot that we have to say before we get there, but this is a good point in showing what the picture is all going to look like. And it's also a good point to mention that because we're going to undo all of our differentiation formulas, not a bad idea to take another look at chapter 3 and just practice a few of those problems. If you feel you're a little shaky on, like, say, the power rule, product rule, quotient rule, there's so many rules, chain rules, and so on and so forth, it might be a good idea to get some more practice on those, because we have to have a pretty good understanding of them to undo them. So that's what we're heading towards. And for the upcoming exam, I feel like the coverage is probably, I'll be explicit about this before Monday's class. I'll put in the exact information. But at the moment, I'm thinking it'll take up right where exam 2 left off on and go up to section 4.4. I don't want to put too much on that exam, and I'm not sure we're going to make enough headway today to really put it on the 3rd exam. So we'll have that all finalized before Monday's class. Last thing to mention is we have a brand new quiz. I believe this one, let me remind myself. I wrote it the other day and I already forgot what it's based on. Okay, yeah, so this one is based off section 4.2, finding out local minimums, local maximums of that graph, which is like practice before doing section 4.4. Well, that's my full spiel of announcements. Any questions, comments, or concerns, those kinds of things folks would like to discuss so far? Okay, well, let's dive on in. We're now section 4.4. We finished example 1. Let's take a quick look at it just to remind ourselves, what does the whole process look like? Thank you. So back to, oh, I forgot to actually open the notes. Here we go. So in the section 4.4, one thing that we mentioned is we are making adjustments to the second derivative test and the first derivative test. The adjustments I've highlighted in the green and the blue that we see here. If we can find that the second derivative is always positive, which we did write down here, then we can conclude that f at the critical number would be an absolute minimum. And that's what we did right here. We built a function, we took its derivative, set it to 0 when we solved, finding 7.5 as the critical number. Now, we could have used the first derivative test, but that would have been working pretty hard. The second derivative coming out positive for all x in the domain tells us right away that critical number led to an absolute minimum. The question said, let's see here, what's the smallest possible value? So we took the 7.5, threw it into the function, and that's that smallest possible value. So our goal is to take a look at more problems like these, but with more interesting context, not just two random positive numbers. Any questions at all, folks, about the process? Okay, I want to mention that these problems are kind of dangerous as exam questions, especially when we do the homework, because to really do a full top-bottom analysis on this kind of problem, a lot of times we forget steps 3 and 4, where we're really using the second derivative test or the first derivative test. If you got the critical number and just plug that into the function, you'd get the right answer in WebAssign. WebAssign has no idea if you use this first derivative test or the second derivative test, but it's required on exams and quizzes. And here's the reason, just as a reminder. There's just never a guarantee that the function, this one that we built, is going to play nice. It did for our case, but we're worried about these kinds of functions. Y equals like x to the power of 2/3. Just a fast one to put it. Let's make it 1/3. That looks a little bit nicer. No, how about 2/5? Geez. There's one function I wanted a little bit more than any of that. Y equals 2/3. 1/3. I'm having a hard time coming up with that function. Let me just cheat a little bit and go back to section 4.1, where I definitely had a good example there. And that's what it was, 5/3. Let's build that one out. So just a little bit of cheating to start out. 5/3. We're trying to avoid this kind of function. And again, there is no guarantee when you're optimizing a problem that you're in this situation. What's happening here is there's a critical number right here. That's a horizontal tangent line. The derivative is 0. So you might decide, say, like on this problem, once you found a critical number, you found the location of an absolute maximum or an absolute minimum, but it's not necessarily the case. And this one had neither a maximum nor a minimum right at 0. It's because of these examples here that we really have to show this for the purposes of exams. I highly encourage you to do that as well on WebAssign. Actually do the second derivative test, actually do the first derivative test, because we'll be required to do that on, again, quizzes and exams have that expectation. So that's why we'll always be very careful with what test we're using and show, like it says, all steps of the chosen test. Well, that's a pretty long reminder of what we did last problem. So let's now go to the new problems. Here's our brand new first derivative test that we took a look at the end of Monday's class. What makes this one a new derivative test giving an absolute maximum or an absolute minimum is the fact that once you find the critical number, the derivative will be positive for all x less than c. It's that for all x that's making this happen. So that means it's always increasing until you get up to c. The derivative is negative for all x bigger than c, meaning it's now always decreasing. And the picture would then look like this. From this end, you're looking at that end of the curve where it's always increasing. From here, you're looking at this end of the curve where it's always decreasing. And that takes you to an absolute maximum. Switch the inequalities and you're looking at an absolute minimum. So this test works when you have exactly one critical number that satisfies those inequalities. Again, those inequalities don't have to hold because here, the first derivative is always positive, 0 at that location, and then positive again. It's the fact that it switches, which proves you really had a maximum and not just some trick like in this problem. With all that said, we're about ready to give this a start. Any questions so far? Okay, so this problem says the rate in milligrams of carbon per cubic meter per hour, so really complicated unit, at which photosynthesis takes place for a species of phytoplankton is modeled by the function below. This is a pretty important problem. It might not be phytoplankton. Maybe we're a grower in California producing lettuce for the nation. We want to optimize the rate at which photosynthesis is going to take place. And for the phytoplankton, here's the function that they're going to be using to model. P stands for photosynthesis. It looks like that's the correspondence there. But the I is a pretty odd unit. I is the light intensity measured in thousands foot candles. Again, that's a real unit, but it's a weird one for light intensity. Usually you're using lumens these days, I think. So we have a function P for photosynthesis. It depends on light intensity. And that makes sense. If there's no light in a room, you can't expect things to photosynthesize. If the light's up too high, though, you're going to destroy your plants. So if you're a grower, there's some optimal value. You would want to optimize the photosynthesis rate for whatever you're growing. That it looks like here, this variable I is going to be the independent variable because photosynthesis depends on I. But let's say a little bit more. Because we're dealing with a situation of light intensity, we would say at 0, that's total darkness. But now negative values may not even make sense. So let's say here, I has a domain, and the domain of it is going to be greater than or equal to 0. This is what would make the most sense in this kind of situation. And it's also the independent variable. Calling it the independent variable is important because we have to now differentiate that thing. And that's tricky when you're differentiating things that don't involve x's and y's like we're used to seeing. But the moment you know it's an independent variable, you can differentiate this by an analogy. You could call this y equals 100x, x squared plus x plus 4. Now, we won't differentiate that, but I'm putting this down just as a kind of a strategy. If you find that differentiating these kinds of functions are pretty tough, fall back to this. Just practice differentiating this one, and it'll help you out tremendously when you go to do the real function over here. Just think of your I as an x, and everything else down here is x's as well. So they ask us the question, let's I guess put a page break, for what light intensity is P a maximum? So let's put down something for us, just to help us out. This is saying, find the value of I to maximize P. Now, the reason I wrote down that statement is sometimes these problems are trickier than you expect, especially in WebAssign. It's not easy to tell what's being asked. In this problem, we want the value of the independent variable that leads to the maximum, but we don't care what the maximum value is. We just want to know what to set the lights to, essentially. In the prior problem, it asked us, what's the smallest possible value of the sum of cubes? That means the answer is not the critical number. The answer is found by putting the critical number inside the original function and getting that output out. So sometimes these questions want the absolute maximum or the absolute minimum. Other times, like in this case, the answer to the question is the value of the independent variable that leads to the maximum or minimum. So that's already very tricky. You could do everything right on this problem in WebAssign, but miss it because you found the maximum value P, which wasn't being asked for. That's super frustrating. So that's a good kind of thing to get out of the way to start. Let's do a screenshot on this so we're not scrolling up and down a bunch. But once we analyze the problem completely, we still have to do the task of differentiate it, set it equal to 0, and solve. That's pretty much the first step of all these problems. Notice example 1 was harder. We had to build the function and then differentiate it. So it's in this sense that example 2 is a little bit nicer. The function's already built. We're just attacking it directly. So here's step 1. Solve the derivative of P with respect to I set equal to 0. Leibniz notation is more often used if you get a function in this form where there's no x's and y's. So I'll use Leibniz notation here, but you could just say just as well, if you prefer, it's up to you. P prime equals 0. So if you prefer to use Newton's prime notation, completely fine as well. But sticking to Leibniz, we're calculating dp di. Next thing I would probably want to do, just to be careful, is let's run this through the product rule. We have to take the derivative of the numerator multiplied by the denominator copied in, then subtract the numerator copied in, but then that portion is multiplied by the derivative of the denominator down there. Only thing I hate about I is it takes us like a half a second longer for me to write down that variable versus x. So those are the two derivatives. Then divide the whole thing by that denominator squared. And we are well on our way. Well, let's start working this out carefully. Even though we're not doing this problem as an analogy, we'll still think of it as an analogy. Right here, when it says derivative of 100i, think in terms of these. You're just doing the derivative of 100x. 100x prime would just give you back a 100, x falls out. And by the similar token, because I is an independent variable raised to power 1, differentiate this, I falls out, and you just carry 100 down. This is definitely very tricky. I want to pause right here. Does that make sense to folks on getting that 100? Okay, looks like so far so good. So let's keep on going then. We have 100 from there, and then the next portion is just copying. Minus and more copying through to this location. Now we hit another derivative, and let's do the same kind of strategy. Sometimes people indicate their derivatives like this. Other times people prefer writing out the derivatives in this format. Indicate the function. But I'm going to write it in terms of x's because they're just more familiar. We've done hundreds of those kinds of derivatives. And then just write down a y prime down under. So differentiating that would give us a 2x plus 1. Now, if we feel comfortable doing this, then we come over here and essentially do the same thing. It'll be from the first term, 2i plus, this is 1 times I. So when we differentiate that, the 1 survives and I vanishes. This portion is constant, so it's gone. And that's the full result for the numerator differentiated. Oh, yeah, that would have been a 1. Thanks for mentioning that. That is definitely not right. We should have carried that exact 1 as well. Thanks for spotting that. So derivative of I turns into a 1, and that's now our correction there. Any questions, folks, so far? Okay, we've got our numerator in, so now denominator squared is I squared plus I plus 4 power 2. Now, this is our equation to solve. And looking at this problem a little bit carefully, it would be wonderful if we could just use the second derivative test. It's fast when it works, but notice this is already hard to get to the first derivative. That's why we're going to actually use that test, the first derivative test. We wouldn't necessarily want to do a higher order derivative on this kind of problem. That's going to make the algebra way worse. It's a longer problem. So since we're doing a first derivative test, we're going to eventually do a number line to analyze, but in solving this equation, we should simplify this function as much as feasibly possible. So first, let's distribute 100 into that group. We have 100i squared plus 100i plus 400. Over here, distribute negative 100i, we'll get negative 200i squared minus 100i, all of which is divided by the I squared plus I plus 4 squared. So we're definitely tracking through it. Next thing to do is to combine our like terms, and it looks like we have a cancellation. 100i combines and cancels with negative 100i. We also have a like term. So altogether, this turns into 400 minus 100 I squared over that denominator. Copying that denominator is kind of tedious, but let's keep on going with it. I squared plus I plus 4 squared. Well, at this stage, this is pretty good for a simplified derivative. Because we're equation solving, we're also going to factor it. And it starts with the greatest common factor of 100 that we can factor out of both terms. So factor out a 100. That will leave behind 4 minus I squared divided by I squared plus I plus 4 squared. So we've got that part down. Next thing is the difference of squares applies once again. I think it's our most used factorization formula by far in this class. So by the red dot, factor that one as 2 plus I, 2 minus I, and same denominator, I squared plus I plus 4 squared. My hand is actually getting tired running through this derivative, but so we know we're just about there. Set the whole thing equal to 0 because we can't simplify it any further. And now the only possible way this equals 0 is if the numerator itself equated to 0. But the numerator is in a factored form, so solving this one is immediate. We can say I equals, in this location you would put in a -2, and in this location you would put in a +2. But now we need to be careful. We did mention already that if we're using the first derivative test for absolute maximums and absolute minimums, we expect one critical number. So the fact that we have 2 means there may be a problem here. Anyone see what the resolution ought to be? Yeah, go ahead. Exactly. Well, if it was a situation like this, I is the light intensity, which had to be positive to begin with, then absolutely, we need to eliminate that -2. It's just not in the domain of what we're trying to analyze. So as a function like this, the one in orange, that would have had 2 critical numbers. So we would have had to use local minimums, local maximums at our analysis. But our real function had a domain restriction, a pretty big one. I cannot be negative as light intensity. And so that's just eliminated. Now that we have one critical number, that shows we're on the right track. There probably is an absolute maximum or minimum. This one is looking for an absolute maximum. We indicated that there for us to find. So let's put down here, I equals 2 is the critical number of P, the photosynthesis function, the original one. So now that step 1 is done, and step 2, we have to apply the full first derivative test, which means we now need a number line. We need to analyze the sign of the derivative on one end and the other to determine if we truly have an absolute maximum at I equals 2. This is tricky work. We did it all in section 4.2, but now that we have larger context, it just feels a little bit more abstract. So let's be careful with it as we go. First thing you want is a number line. And always check your domain conditions on your number line. This is a I axis, not an X axis. The independent variable is I. Light intensity I starts at intensity at 0. So our number line should look like this with that starting value. Next, we found a critical number, I equals 2. So from the I equals 2, just put it down somewhere. So there's 2 in units of thousands of foot candles. That gives us 2 different regions. And that should always be the case for the first derivative test for absolute maximums and minimums. I'll put infinity there just because that's a nice decoration for interval notation. And here's what we're going to do next. Let's just pick a color here. We need a test value in this range. And 1 just seems like the natural choice. You don't have to work too hard and pick a 1.7. Note you cannot pick a 0. Well, You know what? Could you? Why did I say you can't? Looking at 0, 0 is in the domain. That would qualify as a decent test point. Kind of weird to use it as a test point because it's at the end of the domain. Oh, yeah, that's another issue. If it's at the end of the domain, we don't have a definition for single-sided derivatives. So that could be a technicality, but in this problem, the domain would have gone to the left if we used the full function here. So I'll leave it up to you. 0 would work as a test point. A natural test point might be 1. So I'll stick to a 1 on this. That's what you would do in most cases if the domain really ended right here, because our derivatives require our domain to go to the left and to the right. So that's a weird technicality. I'll use a 1 on this issue, or this region, and a 3 on this one. What we're looking for is the sign of dp, di, so here and here. So let's just throw in the values. Take your 1, evaluate dp, di when I equals 1, and our derivative is right here. You can follow the dp di, take the equalities all the way down, and it's right there. But let's also emphasize it, because it's kind of off page where the equality started. So there's the derivative. We're plugging 1 inside, and you'll get 100. 3 and a 1. Putting a 1 there gives us the 3, and a 1 here gives us the 1. Down below, we would get a 6 squared. And this whole thing is positive, so we get to put positive here. That means photosynthesis is increasing this range. Makes sense, right? If the lights are at 0 total darkness, but you increase the light intensity, photosynthesis should go up. But what we were really interested in this problem is the optimal point. Right here at 2, if you keep on turning on the lights, you're going to destroy your plants. They can only handle so much photosynthesis, so much light intensity. So now, over here, our hope is that we get negative. But we've got to show that, so let's take a look. You take this 3 and plug it inside. The powers on these two groups are 1s, so it would in fact flip if you're thinking in terms of multiplicities. But it might be simpler to just crank it out, dpdi. Evaluated when I for light intensity is 3 would give us, we'll plug here and here, so 100. A 5 on the first group. On the next group, we'll get a -1. And down below, it's kind of irrelevant because it's to the power 2. It's going to be positive anyways, but let's put it in anyways. That would be a 3 squared plus 3 plus 4, all squared. And that's, oh, not a positive quantity. That is absolutely a negative quantity, all due to that one negative sign. So we are right if we thought it should flip signs, negative or here, which now means photosynthesis activity is decreasing the moment we went beyond the critical number 2. But again, that's something we have to actually show because the function could have done this. Those have been some resilient plants if the photosynthesis just keeps on going up, so we don't expect it to happen. But we have to actually prove it really doesn't by applying the full first derivative test. At this stage, we're pretty much done. We look at what's happening. If we went from increasing all the way to a 2 and start decreasing, we've just proved that there is an absolute maximum. But we need to double check what answer are we really giving. Sometimes we're taking the value of 2, plugging it back into the original function to find the actual maximum value or minimum value. But this one said, what light intensity takes you to the maximum minimum? So all we're going to do is just state that critical number. So down below here, that's where the thing switches. So we'll say at I equals 2,000 foot candles, photosynthesis activity. It's for those phytoplankton, but we don't have to make a huge conclusion. Let's just keep it terse. This photosynthesis activity has an absolute maximum. Or we could have just said at I equals 2, photosynthesis is maximized. I think it's fun to emphasize we found an absolute maximum altogether. Well, that's the first derivative test. This one wasn't too bad because the derivative didn't have too many moving parts for us to test on, but still is a lot of work. And this is the test that's easy to miss. Web assignment is not going to know if you did it or not, but we still have to do it for quizzes and exams, just for a reminder. So I encourage you to practice this for all the problems because it'll help on the exams. Any other questions or comments, folks, on finishing off this one? Okay, so this one's a pretty practical problem. Even though the model looks like a made-up problem, there was units actually on this thing, but it looks like it was a pretty simplified model. This is really the kinds of things people do, whether they're growing food, farming fish, that kind of thing. They're always looking to optimize. So next thing to take a look at is this example right here. One thing I want to mention is I didn't assign a lot of problems on WebAssign for section 4.4 because, I mean, these are pretty long problems all on their own. Some of them are pretty tricky, so when you go to do your WebAssign problems, I wrote all these questions to be pretty much directly targeting the problems you're actually going to do. So if you get stumped on one, take a look at this document we'll upload later. And if it doesn't help out, don't hesitate to write. Use the Ask My Teacher button or just directly email. I'll be very happy to help out. So here's what's going on in this problem. We have a rectangular storage container with an open top, and we're trying to produce it to have a specification of 10 meters cubed. Who knows what we're putting in there? Maybe it's a refrigerator. Nothing weird's going on. They tell us the length of the base is twice the width. So that's a stipulation in the product being made. Let's do a page break here. Now, you can imagine this is something an entrepreneur is definitely going to have to be faced with in an optimization problem. In building this box, it has that specification and this dimension specification, but we also have material costs we're trying to optimize. The base is $10 per square meter. The sides are $6 per square meter. Kind of makes sense. You want your base to be strong for whatever this box is for, or this rectangular container. And we want to find the cost of materials for the cheapest such container. Makes sense. We want to make it cheap and then market it way up to get a great profit margin on this thing. So this one's a hard one to start. Example 3 is kind of like example 1. We have to actually build this function and we have to come up with a constraint equation that helps us do that. So to me, these are the kinds of questions that are really terrible exam questions. I wouldn't want you to sit around working on building the function. A better exam question would be something like this. You're supplied a function, it can go right at it because it's a timed exam. But these are still really good questions for the sake of homework, sake of quizzes. It could be a good one. So let's work through this by first, in step 1, build the function to be minimized. And the function is an area. It's going to be the cost of materials. So it's going to be a weird looking box at the end because we're going based off cost. It still has to have this stipulation and 10 cubic meters. But the real strategy here is at this point, we really should just draw that box. This is the part I'm terrible at. So I actually Googled this and practiced it before coming to class. It's a good strategy for you as well. So if you're like me and not very artistic, building the box kind of amounts to doing this. Just put down 2 squares. You want to offset one. I'll put this one way out here. Okay, so here's my 2 squares, and then you just go vertex to vertex. So here's one edge. On this edge, you'd want to kind of go dash to just convey some depth to it. You wouldn't be able to see that edge until you're looking through the open top. Then edge to edge here, edge to edge here, and that's about what your box would look like. It could be a little bit better if we were really making it look believable and go, oh, that's not quite right. Let me try again. That would be viewable, and then from here, that part would be not viewable. So our box would look about like that. So the fact that it has an open top is why I'm emphasizing these dashed lines. And that's pretty much the extent of my artistic ability. I can't go too much beyond this. Let's now take a look at this information. We'll have a volume of 10 cubic meters, and that's a constraint. It must have that volume. So that's the constraint equation we're about to build. Volume is 10 meters cubed, but at the same time, volume is going to be the length times the width times the height. So length, width, height is 10 meters cubed. So we've used up this piece of the information from the problem. We definitely have to use this, and this is a good problem-solving strategy. Every portion of the statement in example 3 is important. If we never use this highlight statement, we've probably made a mistake somewhere, or just somehow really did something fancy and got through it. But if you notice there's something you didn't use, that's kind of a red flag. The problem isn't going as intended. So the length of the base is twice the width. Let's call this the length. I drew it longer, so here's the length. This will be the width, and this will be the height. So when width came last, it's a good idea to assign a variable to width as x. Now this statement says length is, well, twice x, because it's twice the width. But sadly, we don't have a statement like this that relates height. That means there's just a whole new variable. I'll call it y. Why not? So we have an x for width, 2x for length, and y for height so far. Now we need to look into material costs, and it depends on what side we're looking at. Because it's an open top, we have front, back, left, right, so 4 sides, and the 5th side is the base. So let's indicate here, cost of the base. To get the cost of the base, we'll first take its material cost, $10 per square meter. Then we multiply it by the area of the base. I'll do some temporary marks here. The area we're trying to calculate is this area sort of highlighted there. Because it's an area, it's just going to be this dimension times that dimension, so 2x squared. So that means the cost of the base is going to be $20 x squared altogether. So we've got that portion resolved. Any questions, folks, with the base costs? Okay, this one is a little bit trickier. The side costs, $6 per square meter, so it's not as reinforced, it's a little bit cheaper, but we don't have equal sides, so that makes this a little bit more confusing to get through. Let's organize very carefully. So cost of the sides. We start by taking the material cost at $6 per square meter. And then let's organize, that's gonna be the bigger skill here. Let's do the front and the back, because the front and the back would have same dimensions. So the dimensions would be a width of x times a height, which is this height of y. So $6 times, well, it's gonna be xy for this front face, xy for the back face, so it's 2xy altogether. Does that make sense to folks on the 2xy? Okay, so that handles the front side, the back side. But wait, there's more. Let's get these marks off for a moment. We also have to discuss the material cost of the right-hand side going this way, as well as the left-hand side going this way. So that's where you'd be using height again, but you're also using length this time, not the width. Also, the right side, the left side are exactly the same dimensions, so we can start by saying plus 2 times, then go 2x times y. So that should be the full description. simplifying the side costs, this turns into, well, let's take a look. It looks like some actual algebra we have to get through. This is 2xy. This one turns into 4xy. So now it's becoming $6 times 6xy. So finally, altogether, we have a material side cost of $36 times xy. It's a degree 2 equation down here and a degree 2 equation up here. So looks like some parallelism. And now remember, we're still trying to build that function. And we want the material cost. So we're not looking for the critical number. We're looking for the output once we plug in the critical number. But here's the major thing we're trying to get to. The cost function for the container is, you could call it a C of x if you like, C to stand for cost, or if you'd like, you just work generically with the f of x. Always make that your choice. We already did a function P for photosynthesis, so let's go back to f of x. Just feels comforting sometimes. It's a total cost, so what we do is we come back up here. Let me take these markings off. We take this and just sum them together. So 20x squared plus 36 xy. Now, if you look at this cost function, there is a slight lie inside here. The only way we're going to be able to optimize is if we have a single variable function. And I try to put down what we want. That's a function with one variable x. But there's a y there. You cannot differentiate this until we resolve that situation. We must return back to the constraint equation and now use that equation to eliminate. Let me see if I can highlight that. We need to eliminate that y and write it in terms of x. Again, exactly the same thing we did in example 1. So coming back to that constraint equation, its length times width times height is 10 cubic meters. So, well, let's just look these up. Length is 2x. Width is just x. Height, we indicated as the different variable y. And that has to come out as 10 cubic meters. I'll drop units for the moment and just write in a 10 on this. So we can solve for y, but first let's write this as 2x squared. Y equals 10. Then divide both sides by 2x squared. We have y equals 10 over 2x squared, which becomes altogether 5 over x squared. So that value for y is just going to plug right back over here. I don't really like the way I highlighted that. Let me see if I can just do this. It might make a little bit more sense. Plug that value for y in that location. So now we have an honest function of a single variable x, where x is based upon the width, but the length was based on that width as well. And the height is also based on that width. So it's kind of interesting how everything is all tied together on nothing but the width. We have f of x equals 20x squared plus 36x times, here's our substitution step, 5 over x squared. And so now next step, f of x equals 20x squared plus, 5 by 36 is going to be something like 150 plus 30, I believe that's 180. And then x divided by the x squared. Well, if you wrote x times x, or divide by x squared as a 1 over x, that's okay. But 1 over x is not something you would ever want to differentiate with the quotient rule. You'd want to convert that to x power -1. And so when you do those kinds of simplifications, really you want to keep your variable x in the numerator. Think of this as an x power 1 minus 2 powers from the x power 2 gives you x to the power of -1. We did it, folks. This was step 1. We have the function that we're going to optimize, and we want the output of that function. Any questions at all, folks, to that stage? I'm just going to put in dollars here, just as a reminder that what the context even was. Okay, in a mathematical applied problem, this is kind of the goal. Everything up here is important, and if you're doing a real problem like this, you're probably given like 5 times as much information as what you see here. The person who wants you to do this kind of work is going to tell you everything about the problem, but you have to cut through the chase. You have to abstract away and build this. If you can make it a purely mathematical problem, all you're doing is a section 4.2 problem. That's our strategy. Reduce everything, eliminate as much context until it looks like we're back in section 4.2. And now that we're here, the instructions for this problem never said what test to use. It didn't say use first derivative test. It didn't say use second derivative test. So when we look at this function, we need to make a determination on our own. And it's always based off this. Is the first derivative and second derivative easy to calculate? If you say yes to that question, you probably do want to use the second derivative test. I would say it's a yes, that's a fast derivative, and it's a faster second derivative. So down below, we'll indicate for step 2, use the second derivative test. Again, we're only defaulting to that test because the derivative doesn't look too bad. If you really like the first derivative test, nothing is stopping you, but I would encourage you to find the path that involves the least amount of work. That way you're going to make the least amount of mistakes, and that's always encouraged. So first step on that second derivative test is to differentiate your function, set it equal to 0, and solve. So we're looking for critical numbers as usual. So we're over here, this would turn into 40x. On this one, power of -1 comes down and multiplies, you get -180. And the power of x is 1 lower, power -2. Observe, it's always worth mentioning because this can really bog you down in calculus. If you simplify this as 5 over x, you may have used the quotient rule, but that's heavily discouraged. It just takes way too much time. And now you're fighting with little minutia when you really want to just use and focus on the second derivative test. So simply writing out that, it didn't look like a big deal, but it's a humongous deal. And if you can calculate your derivative fast, then you're focusing on the major concepts and not getting bogged down on little minutia. So there it is, first derivative. We now set it equal to 0 and solve that thing. But solving that derivative is kind of interesting in its own right. The way I would probably do it is, let's add 180x squared to both sides. You now have a 40x equals 180. I said x squared. I should have said x to the power of -2. Now, next step you could take is, let's put that exponent in a better position. For equation solving, it's nicer if that's a positive exponent. You get 40x equals 180, and the fix on that is just drop it to the denominator, and that changes the sign of the power. It's now a power +2. The reason I like this format is I'm visualizing this now as a cross product. X squared multiplies here, giving you x cubed. If you're not a fan of cross products, visualize it this way. Multiply both sides by x squared. You're clearing the denominator either way you visualize it. And what will happen is on the right-hand side, x squares are gone. You just get 180. On the left-hand side, x squared combines with x. We now have 40 x cubed. So that massively cleans up this equation right here. It's a complicated looking one. Some people might have done this differently and just taken this and multiply the whole thing by x squared. You'd get the same exact effect. Now, this is the point at which I personally definitely need a calculator. I'm taking 180 divided by the 40. Looks like a nice clean 4.5. Sometimes it's an indication the problem looks like it's going according to plan because it's a nice clean number. That doesn't have to be the case. Sometimes it could be a little bit worse. But we're lucky we get x cubed equals 4.5. So the next step in the second derivative test is fully solve for that. And let's move this way down by taking the cube root. So we get x There's no positive or negative if you're taking an odd valued root. So this will just be cube root 4.5. And this is the critical number of f. So we've got a critical number down. That means in the second derivative test, all we now need to do is differentiate this a second time. And we have to argue that that second derivative is always positive or always negative, depending on the direction we're optimizing. Now that's pretty tricky because if you're thinking of the second derivative test as we did it in section 4.2, this is worth emphasizing because it's so jarring, I'd say. We did it a lot different. In this section, we calculated the first derivative, we set it to 0, and we found the critical numbers. But we were looking for local minimums and local maximums. And so what you do then is you put the critical number inside the function. So that's what we did. When the function for the second derivative was negative, we found a max. When we put the critical number in the second derivative and got positive, we found a minimum. But none of that actually applies to us. It's kind of awful. What we have to actually do, because we're using this method, is we need to either show the second derivative is always positive, not just at the critical number, but for every x, or that's always negative for every x to get the maximum. I believe we're minimizing, for our problem, we're minimizing cost. So some way, somehow, we need to show that direction. Always positive, no matter what. So coming down the problem, if we can't do that, oh, that's the wrong set of notes. If we can't show the second derivative is always positive, this test has failed and we have to default to the first derivative test. That's kind of awful whenever it occurs. So now here is the moment of truth, second derivative of f. Here's the first derivative. So second derivative would come out as a 40. Over here, -2 multiplies -180 and gives us plus 360 x power 1 less, so -3. Now looking at this, we need to show that is always going to be positive, so we have an absolute minimum. We've minimized cost if that's the length of the width. Sometimes those arguments are hard to show, and you have extra things available to you if you're doing this as a homework problem. We could just say y equals 40 plus 360 x power -3. And where did our graph go? Well, that's already a concern, right? This is a weird graph. Oh, this is the second derivative, so it's, there we go. We're looking for positive values over here. But notice what I said should happen is already failed. We have negative results down here. So it looks as if the second derivative test did not work. We need to show that this was always positive, not negative. But there is a fix to this. Anyone observe anything special about x itself? No worries if you're not sure. These problems get so long, it's easy to forget the context. But that x, well, where did it come from? It came from solving this equation on the first derivative, which came from this original function, and keep on going backwards, it's a width. So something we probably should have said at the very beginning, but we neglected to say so, is there is an honest domain here. X should be strictly bigger than 0. I'm avoiding saying bigger than or equal to 0 because if width is 0, we don't exactly have a box, right? So I made it strictly bigger than 0. Now that's a restriction on the original function f of x. Let's put it here. X is greater than 0. And so coming back down to the second derivative, recall, if x is greater than 0, then in the graph that we took a peek at, none of these values actually matter. The negative values are irrelevant. We are on this end of the curve, and it settles down to an asymptote at around -40 pretty rapidly. In other words, if you're only throwing in positive numbers inside here, this whole thing is always positive. So we can say now that this is greater than 0 for all x in the domain of f. So that means the second derivative test is actually working. It just is tricky at this very start. We always need to think of domain and range in an applied problem, or excuse me, domain rather. So now that we have greater than 0 right here, in the first derivative test, we have a conclusion. This shows f, the original cost function, at the critical number of f, cube root 4.5, is the absolute minimum cost of the container. But notice what I've done, I really have not solved the problem, right? Sometimes what they wanted is the width x that would have given us the minimum cost, but the problem itself explicitly said, what is that minimum cost? So we have to calculate this thing. So this is a good one for the calculator as well. And this is one issue where it's always good to emphasize what function did you calculate? This one's the second derivative, so that's wrong. We want the original function. We don't want this one. We want that right there. So labeling your functions as you go is survival at a certain point when you have so many functions that you're taking a look at, 3 of them for this kind of analysis. So the minimum cost is going to be 20 cube root 4.5 to power 2, and then plus 180 cube root 4.5 to power -1. This comes out in dollars. We'll round to the nearest cent, which is a natural rounding position. And now just chuck it all into the calculator. Let's see what this results in. Actually, it's kind of a tricky one to really calculate. So one thing I want to remind folks on a real exam is if you put this down on paper on your exam, before you put it into the calculator, you get a lot of partial credit, essentially all of it. So if you make a simple mistake on exams, maybe you're a little bit nervous, your fingers are shaky, you have great protection by writing this down. This one's a tricky one to put in the calculator. I would put it in as 20. And now a cube root is really a power of 1/3. So this is easier to put in as 4.5 to the power of 2 because we're squaring it, divide by 3 because you're doing a cube root. So you'd want to put it in an exponential form, I think is the easiest way. That's going to be plus 180. Same thing here. This will be 4.5 to the power of, you take the numerator power, -1, divide by the index of the root, 3, and this is the result we would get. Turns out this box is going to cost $163.54. And depending on how you decide to estimate this, not a bad idea to give a really conservative estimate, because if you're doing this for a client, you wouldn't want them to be disappointed. You might round to the next nearest cent or the next nearest dollar. But for WebAssign, we have to be careful. Give it the nearest cent always, rounded, and you're going to be safe in WebAssign. 163.54. Kind of an expensive box. But anyways, we've got it, folks. That's the optimization on this problem here. Any questions at all, folks, on getting through this one? Kind of hard to zoom out enough to show the whole thing. We don't rarely do problems that take up essentially 2 whole pages, but this is one of them. Section 4.4 just involves really long problems. And the more math you take, the more this becomes just part of reality. The math gets longer as you go further and further into your course or your programs. So the next one we want to take a look at is this one here. This will be the final one for the notes. And looking at the time, let's see here. We've got about 15 minutes and some change. I think we can make a good start at this one. Let's take a look. It starts off by saying the blood alcohol level in milligrams of alcohol, I would assume, per liter of your blood, T minutes after consumption of a hard liquor is given by the so-called surge function. In pharmacokinetics, a surge function is just how your blood responds to something new in the system, whether it's an injection or taking a shot of something. So here's the function that models B for blood alcohol level, T for time after taking whatever amount of hard liquor that was. It didn't specify. But the question is, if you took this shot of hard liquor and this function accurately models how your body responds to your blood alcohol levels, you'd want to know at what time is the blood alcohol level at its peak. What's the practicality of this problem? Well, I'd say this would probably be interesting for something in court, for example. If they can prove how your body responds to alcohol, they might be able to establish a timeline of Mike Jacobson was this inebriated at 6 o'clock, and that makes this crime more likely. That's probably the context where something like this could happen. So let's give this a try. What makes this problem not so bad is, notice, functions just immediately provided to us. That's nice. What's not so nice is when you look at this function, let's color code this up. We have a function here multiplying some other function, a base C exponential. And so this one is automatically going to be using product rule. If you notice that you're going to use fancy differentiation techniques, quotient rule is a bad one. Product rule can be pretty nasty. You probably don't want to use the second derivative test, because even if you do calculate the second derivative on this thing, note what you must do is you have to establish an inequality like this one right here. And sometimes that is extremely hard on the second derivative test, showing that equality is always true. So for me, my strategy is the moment I notice any extra difficulty in differentiation, I automatically default to first derivative test. So let's use that here. So my steps on this problem are just going to be the steps you would take on a first derivative test. Step one, well, you definitely have to differentiate the function. So we go back over here. Because it's written as B at T, you might use Newton's prime notation, would be pretty appropriate for this one. So blood alcohol content at time t differentiated would be first, differentiate that function. Think of the t as an x if it helps out. The derivative of a t power 1 will just give you the constant, 29.6. But this is also a product rule, so 29.6 gets multiplied by that function. I'll put it in black to signify no differentiation on it. Just copy an e to the power negative 0.1095 times t. Plus for product rule, kind of makes sense, p for plus. Next, copy in the first function, 29.6t. Then differentiate this function. And right there, we should probably pause because differentiating that function is chain rule, further indication that maybe first derivative test is the right process. So let's do this one carefully. If y equals e to the power of negative 0.1095t, we have a decaying exponential function. We didn't do functions like this in the exponential growth, exponential decay section because what made it a surge function is that variable t right there. It's not your ordinary exponential function at all. So now analyzing this one, we have e to the x is the outer function that we'll handle first. And all of this stuff here, that's the inner function we'll handle second. I think it's a good idea to do this one really methodically because usually it's just trickier to do chain rule on exponential functions and logarithmic functions. So this will become a y prime equals, and I don't want to get too close. Let me put a little border here. So y prime is going to be equal to on this one. First, here's the chain rule format. Second, input the inner function into both placeholders. And I really did make that big enough. Let me expand just a touch. So we'll go up here in the base C exponential and then down here. So just about there, folks. I typically drop parentheses there. I just put it in to show a pattern. I usually like to put this in front of the function. So the derivative of that portion will give us a negative 0.1095 multiplied by e, so the power of that thing there by the red dot, negative 0.1095t. So all that work was a result that goes here. Back to the product rule, we differentiated, copied, and we copied this one, and now the derivative of this plugs in as, we'll need parentheses because of the negative coefficient, negative 0.1095 e to the power of negative 0.1095t. So we're just about there. We want to simplify this as much as possible. But any questions at all, folks, to finish out the product rule plus chain rule as well? Yeah. Oh, thanks for spotting that. That is my dyslexia showing once again. That is a 26.9. Oh, my eraser is acting weird. Let me see if I can fix this. This mistake definitely didn't even want to come off of the page for some reason. Thanks again for spotting it. 26.9 in this location. And I did again over here, looks like 26.9 over here as well. So the derivative of that came in as 26.9, not 29.6. Weird typos. Those are the kinds of mistakes that become invisible to me because I'm the one that made them. Thanks for spotting it. Other questions so far? Okay, let's now simplify this derivative. So b prime at t is going to be equal to, now the simplification of this, I would say should involve factoring right out of the gate. I wouldn't necessarily want to do too much without doing that step. And notice you do have a common factor here and here. Factor out e powered negative 0.1095t. It's essentially a cancellation. I'll put this as a temporary mark to assist. And we just bring down what's left behind. 26.9 plus these two multiplied together. I'll make that a next step to show the multiplication. And feels like I'm missing one other thing. Yes, absolutely. Sorry, not sure when I deleted it and fixed it, but when I fixed the number, I neglected to bring down t. That should have came down as well. Sorry for that omission. So variable t should be in this location. And now that looks a little bit more correct. Boy, copying all that down can be kind of an arduous task, but we're getting there, folks. That's the factorization step. So next, b prime at t is e to the power negative 0.1095t multiplied by, let's grab our quick calculator here. I need a 26.9 times 0.1095. Comes out as that quantity, and I'll just throw a negative number in front of that. Negative 2.94555. I'm not going to remember that. Let me try again. 2.94555. T. And that's finally our derivative in its most simplified format. We're about ready to run through the full first derivative test. I'm noticing this one is probably not something we can do at about 5 minutes. So this will be a problem that we'll come back to when we're on our Monday's class next week. We'll finish up the analysis on this one and then move over to the section on antiderivatives. But any questions on what we have so far to this stage? Okay, if you'd like to keep going on this one, we can compare our notes when we come back on Monday. the next steps would be set it to 0 and solve. But this one has no bearing on the problem. You're really setting just this portion equal to 0. That's because the base exponential function is never 0. You could even just divide it out if you wanted to. Once you set that equal to 0, you'll have a value for t. And then you have to do this. T does have a natural domain. At 0, that's the moment, the instant in time before taking that alcoholic beverage. And at positive time, it's now affecting your blood. So we would do the analysis here, where the critical number goes in that location, and we run through the rest of the test. But I don't think we can do that in 4 minutes or so. So any last questions, folks, before we call it a night? Okay, well, this will be our stopping point. When we come back on Monday's class, we'll be finishing off these notes here, and we'll also see on the Moodle website the information we expect to see for our typical exams. I'll be posting that over the weekend before Monday's class. But try not to do work too hard if you can help it. I'll see you all next week.
Thank you.
Yep, have a good one. Yeah, absolutely.
So this
Thanks, you
is
too.
just the normal equation. I got all the answers up until the inflection and I can't figure it out.
Gotcha. So let's take a look. So derivative is 6x squared, 6x, 336. Kind of a nasty one to factor up, 7 and 8. And then now going for, on this side, we're looking for a concavity and inflection, you were saying?
Mhm.
So here's our first derivative copied in. Now it's 12x plus 6. So we have a critical number to this function at -1/2.
Mhm.
So inputting -1 here, we're going to get a negative value. So that's concave down.
Because I have there.
Yeah, concave down looks good here. This one you're putting in 0 positive, so concave up from here. That looks great. So your inflection should happen at -1/2. So that looks good. And so, geez, I don't see any issues with the work.
I kept putting in different answers and it kept coming up wrong. So I was
Strange. Let me see if I can find a way to reverse engineer that. So -1/2 is going in.
I also put it in fraction
There.
too. And it didn't want to go into a fraction.
Oh, weird. So 2 -1/2 cubed 3 cubed plus, there it goes, 3 -1/2 squared. That's 336 -1/2. I get -168.5 on this one. Potentially that's the issue.
Maybe.
They should have taken this because this is coming out as an exact value
Mhm.
altogether. Let me complete that just to make sure I don't have anything weird going on. Yeah, it might have been just some really small mistake in the calculator that led us off.
I was so close.
Dang it, yeah. WebAssign is just cold and heartless when it comes to that, unfortunately.
And then your office hours are 3 tomorrow? Or
Yeah.
in the student success center?
Yeah, I'll be over there 3 to 5.
Try and be here a little bit. I'm going on 3.7.
Oh, God. Oh, the logarithms. Yeah, that one's been pretty tricky.
I don't know why I'm struggling so much.
Gotcha. I'll be very happy to help out.